Hey guys, so we're going to go over question 3.5 for this how-to-dio. This problem, we're given a substrate here and a film that we're trying to bond to the substrate by using a radiant source, which is providing a heat flux directly to this bonded surface here. In this question, we're being asked to show the thermal circuit representing the steady state heat transfer situation, calculating the heat flux that is required to maintain the bonding surface at a certain temperature, and then we also are going to compute and plot the required heat flux as a function of film thickness between those bounds. As a summary, we're given these variables here, and again, we're being asked to find the thermal circuit, Q double prime naught required, so T naught is equal to 30 or 60 degrees C, and we're also going to plot that heat flux as a function of temperature. So some of the assumptions that are important to this problem is that we are assuming steady state, 1D heat transfer, constant properties. We're going to neglect radiation. We're going to assume no heat generation in the part, and also assume uniform convection over the surface, over the top surface. In our problem, we have a driving force of this heat flux, Q naught here, and it's being applied directly to this bonded surface of T naught, which has a temperature of T naught. Then we will have a substrate that heat has to work its way through, and a film that heat has to work its way through. So we have two branches. Although they're in parallel here, they're really separate entities. So we have that R double prime S, which is the resistance of the substrate, to get to T1 has a heat flow of Q double prime S. And then we have in series a conductive resistance through the film, and then a convective resistance of from the air blowing across the top of it, and that's represented by this branch of the thermal circuit here. All of these resistances are detailed here, where for conduction we have the length over the conductive constant, and for convection we have 1 over the convection constant, which gives us values as seen here. Putting this all together, we have that Q naught is equal to QF plus QS, just balancing out the input with the outputs of this thermal circuit. And we know that QF, or Q of the thin film, is 1 over the resistances added in series times the temperature here, and QS is 1 over the resistance, since there's only one of them, times the temperature difference here. Solving these problems, plugging all the variables in, we can get that Q double prime naught is equal to 2,833 and 33 watts per meter squared. Now, that is A and B, but we still need to plot the heat flux as a function of temperature. So in order to do that, we're going to define all of the variables here in MATLAB, setting the thickness of the film to be between 0 and 10 to the negative 3 in increments of 0.1 times 10 to the negative 3, just so that we're all in meters. We're going to calculate the resistances using this as a vector, so LF over KF, 1 over H, LS over KS. Calculate the heat fluxes, 1, 2, and solve for Q naught. Essentially just doing this process, but iterating for various thicknesses here. And then I'm just going to plot my thickness and my Q naught here. So in this plot, we have the thickness of the film from 0 to 1 times 10 to the minus 3 meters, and the heat flux going from about 2,000 to about 3,500, in watts per meter squared. And we can see that this kind of tapers down in a parabolic manner. And that is my solution for question 3.5.